Here are solutions to homework set number 6 for ECE 341. This homework looks at LaPlace transforms and continuous probability density functions. Now, the first problem looks at LaPlace transforms. Suppose x and y are related by a function of s. S is the LaPlace operator. What is the differential equation relating x and y? Now, the assumption behind LaPlace transforms is everything is in the form of e to the st. What that does is when I differentiate, I get s e to the st. So s means derivative. That's an s. So cross multiply it all out. S squared means the second derivative. S means the first derivative. And y just means y. Sx, there's an s. S means derivative. And x is x. Part B, if the input is a sine wave, find the output. This is where phasors come into play. This is true for all s. In this case, I want to know what is the gain at s equals j5, the frequency of the sine wave. The input in phasor notation is 3 minus j2. The real part is cosine, minus j is sine. So this is how you represent x. Multiply it all out, I get a complex number. The real part's cosine, minus j is sine. In part C, if my input is a unit step, find y. So in that case, this is the relationship between x and y. Replace x with this LaPlace transform. That's the LaPlace transform for y. To solve, I use partial fraction expansion. So for I know I have something over s plus 5, something over s plus 8. Using the cover-up method, if I cover up the s, analyze at s equals 0, I get 0.75. If I cover up the s plus 5, analyze at s equals minus 5, I get minus 1.33 and 0.58. Taking the inverse LaPlace transform, this is 0.75, minus 1.33 e to the minus 5t, plus 0.58 e to the minus 8t. Problem 2. If I have a transfer function with complex poles, not a whole lot changes. Take the transfer function, cross multiply out. S means derivative, so there's the second derivative, first derivative, and y. First derivative of x and x. There's the differential equation that relates x and y. Same as that, just another way of writing it. If the input is the sine wave, again, it doesn't really matter. S equals j5, here's the gain everywhere. This is the gain at s equals j5. The input is 3 minus j2, 3 cosine, 2 sine. Multiply it all out, I get a complex number. Real part's cosine, minus j is sine. So with LaPlace transforms, I can analyze filters, circuits with sinusoidal inputs. That's one use for them. Oh, one last part. For part C, if I have a step input, replace x with a step, do the partial fraction expansion. In this case, you get a complex number. Inverse LaPlace transform, here's the 0.81. These two convert as double the amplitude. That comes from Euler's identity. The real part is the exponential. Complex part is the sine wave. And turns out it's the phase over the minus j term is your phase shift. Problem 3. LaPlace transforms also work for probability density functions. In stats, these are called moment-generating functions. They're also just LaPlace transform. It depends upon your major. They have a different name. It's the same thing. So if this is my PDF, this is not a valid PDF because the area is not 1. To make the area 1, I have to multiply by a scalar. So I can kind of figure that out. This triangle right here, the area of a triangle is 1/2 base times height. So this is 2 times 0.8, 0.4, times 1/2 is 0.2. That's this area. 2, 1/2 base times height. 2 times 0.8. I didn't do that right. 1/2 base times height. So that's 2 times 0.8 divided by 2 gives an area of 0.8. This right here has an area of 0.8. And this has an area of 0.2. So add them all up, I have an area of 1.6, 1.8. So to make the area 1, k is 1 over that. 0.5555. Problem 4. Find the corresponding CDF. So the CDF is, I take this point x and I start sweeping it right. What's the area to the left? So pretty clear, if I start left of 1, there's no area under the curve. So the PDF is, well, CDF will be 0 for x less than 0. To find the rest of the terms, I'll come up with an expression for these guys. And I'll do that using piecewise linear functions. So between minus infinity and 0, it's 0. Between 1 and 3, it's this line, that's the slope, 0.4 times x minus 1. And kind of one trick I'm doing is the slope is 0.4, changed in y over change in x. Set up so that I'm 0 at 1. That's why I wrote it in this form. Between 3 and 4, it's 0.8. Between 4 and 5, it's 0.2. Between 5 and 6, is 0. So there's the PDF times 0.5555. So the CDF then is integrate. When I integrate 0, I get 0. Integrate 0.4x gives you 0.2x squared. Integrate minus 0.4 gives you minus 0.4x plus a constant. To find the constant when x equals 1, I should get 0. It needs to be continuous in x. So I'm going to go left at 0, at 1, then it starts going up as a parabola. Between 3 and 4, the integral of 0.8 is 0.8x plus a constant. To find the constant at 3, it's got to match up with the previous function. And you wind up with minus 1.6. Between 4 and 5, the integral of 0.2 is 0.2x plus a constant. The constant is matching up with what is between 3 and 4, and above 5, integral of 0 is just a constant. And that should be 1.8. So that result, when I solve, the CDF equals 1. All probabilities add to 1 eventually. In terms of programming it. So if we take x between 0 and 6, if I come up with a function in MATLAB that does this, given x, find the CDF and plot it, here's what you get. And kind of notice, at 1 it's continuous, at 3 it's continuous, at 4 it's continuous, and 5 continuous. The slope might change, but it's got to be continuous. So there's my CDF. Problem 5 is find 20 values of x that meet that PDF. So one way to do that is I'm going to use interval halving, because it's easy. I'm going to pass my probability, number between 0 and 1, at 0.6, come over and find that point. To find that point, what I'm going to do is do interval halving. My first point is 1, the second point is 5. Keep on taking the midpoint and replace the two endpoints, repeat 20 times, and when I'm done, whatever you wind up with for x3 is what's returned. So once I have that function written, called problem 5, completely original name, I'm going to guess a random number for p, and then convert that probability to x. So when p is 0.27, x is 2.7. P is 0.78, there's x. And what you're kind of doing is going along here. When p is 0.27, I come over, and there's x. When p is 0.78, I come over, and there's x. Repeat 20 times. And just for fun, if I plot x and p, they wind up on the CDF. It's got to wind up on the CDF. So this right here are 20 variables that satisfy the CDF, that satisfy that PDF. So basically the CDF is actually kind of useful. I use the CDF to generate variables of a given distribution. I use the PDF to describe the function. Again, like this is actually easier to see what's going on, the PDF versus the CDF. Finally, given this PDF, find the moment generating function, or in other words, find the Laplace transform. There's a couple ways of doing that. One trick is take the derivative until I get delta functions. I like delta functions. I know what the Laplace transform is for delta function. So here's a delta of minus 0.8. So this is going to be minus 0.8 times 1. The Laplace transform of a delta is 1. Delayed by 4 seconds, e to the minus 4s. Here's the delta function with an amplitude of minus 0.2. So this is minus 0.2 times 1, e to the minus 5s. I still have the stair step, so take the derivative again. I get a delta. So what happens is these guys become this. I have a delta function amplitude of 0.4 at t equals 1. Delta function amplitude is minus 0.4 at t equals 3. That's when I differentiate twice. To get back to the original time, integrate twice. And integral is 1 over s squared. For these functions, that's right here. Really didn't do that right, 0.6. That's my two delta functions. Integrate once. So there's the Laplace transform of this guy. And that is homework set number 6 for 341.